Welcome back to Arxflix. Today, we're diving into a fascinating paper that challenges our understanding of transformers. It argues that these powerful models, often seen as distinct from recurrent neural networks, RNNs, can actually be viewed as a specific type of RNN called a multi-state RNN, MsRNN. Let's start by understanding the core idea. The paper proposes that decoder-only transformers, which generate text autoregressively, can be seen as MsRNNs with an infinite number of states. This figure illustrates the concept. The top part shows how a transformer can be viewed as an infinite MsRNN, where the key value vectors represent a dynamically growing multi-state. The bottom part shows how transformers can be compressed into finite MsRNNs by limiting the number of tokens processed at each step. This means that as the model processes more and more tokens, the size of its hidden state, represented by the key and value vectors, keeps expanding. Now, the paper explores how to convert these infinite MsRNNs into finite ones. This is crucial for practical applications, as infinite memory is not feasible. The paper examines existing compression techniques like window, window-I, and H2O, and frames them as methods for converting pre-trained transformers into finite MsRNNs. But the authors don't stop there. They introduce a new compression policy called TOVA, token omission via attention. TOVA is simpler than previous methods and makes fewer assumptions. This figure shows how TOVA works. It keeps a fixed-size multi-state, and at each decoding step, the state with the lowest attention score is dropped. TOVA focuses on the attention scores of the last token, making it more flexible and less biased towards recent or early tokens. The paper evaluates TOVA on various long-range tasks, including language modeling, long-range understanding, and text generation. The results are impressive. TOVA consistently outperforms other compression policies and achieves performance close to the full model, even when using only a fraction of the original context size. This figure shows the perplexity results for the PG-19 language modeling benchmark. TOVA outperforms all other policies across different multi-state sizes, while maintaining comparable results to the full context model, using only a quarter or even an eighth of the context size. The paper goes further and analyzes how TOVA selects tokens to keep in memory. This figure illustrates the tokens kept by TOVA in the last layer of Llama 2.7 on a PG-19 example. Each row represents a decoding step, and each column is a token attended to. The analysis reveals that while recency is important, TOVA also keeps older tokens, especially the very first token in the sequence. This suggests that transformers, even when compressed, retain crucial information from the early parts of the input. This research has significant practical implications. By compressing transformers into finite MsRNNs, we can dramatically reduce memory consumption during inference, leading to increased batch sizes and improved hardware utilization. This opens up possibilities for deploying large language models on devices with limited memory resources, making them more accessible to a wider range of users. Overall, this paper provides a fresh perspective on transformers, highlighting their connection to RNNs and offering a new way to optimize their performance and efficiency. Thanks for watching Arxflix. Don't forget to like, subscribe, and share this video with your fellow researchers. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.